Hello everyone, welcome to Organolysis. Now welcome to another video of the name reaction series. Now in this particular video we are going to discuss the Barton Nitrite Ester reaction, right? So in this case, the first of all the alcohol, a kind of alcohol is used, and the first alcohol is going to convert it in this nitrite ester. So that is why the name is the Barton Nitrite Ester reaction. So we can modify and we can convert this nitrite ester by using this NaCl pyridine, and after that if we use an HU in this nitrite ester medium, then we will get this gamma hydroxy kind of intermediate. Now how we can get this gamma hydroxy oxime type of intermediate, that is one kind of 1,5 hydrogen abstraction is going to take place in this while doing this reaction, right? So first of all, we should know some key features of this Barton nitrite ester reaction. Now, what is the key features of this Barton nitrite ester reaction? Number one, we already knew that this is 1,5 hydrogen shift. So this is 1,5 hydrogen, not shift. This is 5 hydrogen abstraction, right? We can also call it as a delta hydrogen abstraction. So this is your delta hydrogen abstraction. Now the next point is the stereo specificity. So this is a stereo specific reaction. So that is why this is called a stereo specific reaction, right? So this is your stereo specific reaction. Now we should know the mechanism first, and how this reaction is going to take place. That is, we all know that how we can convert this alcohol to this nitrate ester by using NaCl pyridine. So if we take, I'm writing over here, if we take any alcohol like this, and if we placed pyridine over here, we know this takes a proton from here and it will go like this. So we can write this O minus over here, and if we use NaCl in this medium, now this O minus will attack on the nitrogen center and it will leave from the system, and it can generate this ONO, that is your desired nitrite. So this is your nitrite ester, right? Now the main focus of this reaction is this HU condition, that is your 1,5 hydrogen abstraction or your delta hydrogen abstraction. Let's see that mechanism. So that is quite important while doing this reaction, right? If we take this alcohol, that is, we can write this nitrite ester, that is basically we are going to start with this one, right? So if we take this nitrite ester, so we can write this nitrite ester in this way. Here is your oxygen, here is your R group, and here is your hydrogen. Now the first thing of this reaction, when we use this H2 in this medium, so it will form the homolysis first. Now what is the homolysis meaning? That is, this bond is break in this way. So it will generate this oxygen radical over here, and we can write this in this way. So this is your hydrogen over here. Now the important thing is that, so this oxygen radical, it takes a proton from this 5 number position. So if we numbering from over here, this is your 1, this is your 2, this is your 3, this is your 4, and this is your 5. Now you can also write this in this way. That is okay. Let me do. So if we take, if we call it as the alpha position, this is your beta, this is your gamma, and this fifth position is your delta. So this is how we can also form this delta hydrogen, that is your delta hydrogen or 1,5 hydrogen abstraction, right? Now if we do, that is 1,5 hydrogen abstraction, that is this oxygen takes proton from here and this bond is going to break like this. So the next intermediate, that is your OH over here, and we will get this radical in this position. Now this radical is now combined with this NO, that is, if an NO radical is leave from this here, from this system, this NO radical will leave. So this radical is now combined with this NO radical in this way. So it will form this nitrite ester, that is your OH over here, 1 2 3 1 2 3 4, and here is your 5, here is your R, and this is your N double bond, right? So this is how we can generate this kind of nitrite ester. So this is your overall Barton nitrite ester reaction mechanism, and this type of nitrite ester is going from this tautomerization. So this is a tautomerization form, that is we can write in this way, that is double bond in OH, and here is your R. So this is double bond OH and R, right? So this is your overall Barton nitrite ester reaction and their mechanism. Let's see some examples that is quite important while doing this reaction, and this stereospecific point is quite important, and we will do some examples on it. Let's see some examples first. First, the example that we have this kind of primary alcohol, and along with this there is NOCl pyridine is given. So we know that this nitrite ester is going to form over here, so we can write this in this position, that is your nitrogen over here, and here is your ONO, that is your nitrite, and here is your CO2 group, is your double bond, and here is your N3, right? Now we know that the 1,5 hydrogen abstraction is going to take place, or the delta hydrogen abstraction is going to take place. So this is your alpha position, this is your beta, and this is your gamma, and here is your delta position, and this is your delta hydrogen. So we know what will be the major product if we use this H condition or into atmosphere. This is will form this nitrogen over here, and here is your double bond, and here this CO2 AB group, and here is your, after the tautomerization it will form this NOH, and this is your OH, sorry, this is your CH2OH over here, right? And here is your N3. So this is your major product while doing this reaction. Now this next question is I was came in the CSIR NET December 2016, and this question is important because this is your stereospecific question. Now this example contains the stereospecificity, right? So if we take this kind of nitrite ester, if we place this H nu, you can see over here, this is your alpha position, this is your beta position, here is your gamma, and here is your delta hydrogen, right? But if you go over through this carbon, so this is your gamma and this is your delta. Now the question arises that which delta hydrogen is going to abstracted during this Barton nitrite ester reaction, right? So when we use this H nu, you can see over here this bond is up phase, right? But this oxygen, ONO, that is a nitrite ester, is in below the plane. So stereospecificity, that means indicates that this the hydrogen which is in below the plane, because this is and the nitrite ester is below the plane, so that is why this hydrogen is also going to take place from the below the plane hydrogen, right? So this bond is below the plane, so that is why this hydrogen is going to take place, not this one. So this remains as intact. So the major product of this reaction is this one, that is, and here is your OH, and we can write this over here. You can write over here, that is N double bond O, and this group is remains, right? And after the hydrolysis of this reaction, it will readily tautomerizes. So it will readily tautomerizes to form this oxime over here. Here is your below the plane OH, and here is your double bond NOH, right? And this rest part is like this. And after the hydrolysis, it will form this ketone over here. So it will form the ketone in this position, particular position, right? So we can generate this one, and here is your rest part, and it will form this double bond O in this position. So this is your major product of this reaction. This question came in December 2016, and this question is also was also taken from this Laszlo Kurti book. Sorry, so this is your Laszlo Kurti book, the strategic application of the name reaction, right? So let's see another example of this reaction. Now this reaction is quite important, and this is also the case of the specificity because this is already given in the form of this nitrite ester, and if they have used this only H nu. Now this reaction is important because of this radical trapping, that this radical is going to form over here. So this is a experiment reaction of the trapping of this radical. If we use this H in this medium, so this is your alpha position, this is your beta, this is your gamma, and here is your delta hydrogen in this case. So it will abstracted over here and it will form this one, right? So it will form the OH and it will form this CH2 radical. Now this it will, if this will form the CH2 radical, and if we use this kind of Michael acceptor, then it can form in this, it can break in this way. So we can write over here that is Cn, these two radical in this way. Now this radical is quite stabilized due to this cyanide group, and this radical is react with this CH2 radical, right? And after that it will form this kind of, this is your an OH and here is your cyanide, right? And here is your radical that is present over here. Now this all methyl groups in this position. Now this radical is not going to place over here. Now if we are already reducing, we are already remove this NO over here, NO radical. Now this NO radical will react with this radical. And finally we will get this kind of product, that is your OH over here, and here is your cyanide, and here is your NO. So this is your major product of this reaction. Now let's see last example, that is this one. Now if we put this NOCl and pyridine and HNO in this medium, we know that it will form this ONO. I am writing this OH, remove this, and it will form this ONO in this case. Now when we use this HNO, now there is a two possibility of this delta hydrogen, that is this is your 1 alpha, that is your beta, this is your gamma, and here is your delta, that is delta hydrogen. And similarly if it goes over here, that is your beta, this is your gamma, and here is your delta. But in this case both this methyl group is in above the plane, so that is the specificity remains in both the cases. But if we use this if we generate this position radical, that is CH2 radical over here, and then if we use this COH NaO2, then we will find a 6-membered cyclic lactol type of intermediate. I will show you over here that if we are going to get this kind of product, say double bond, here is your this is your race part. I am not writing this over here. Here is your CH2 radical. Now this CH2 radical takes this NO group over here, so it will form this NO in this position, and it will form this OH, and here is your methyl in this case. And then if we use this ACOH NaNO2, it will form now it can tautomerize. Now it can, if it can tautomerize, then it will form this OH, not this one, this C double bond N OH, and after this hydrolysis it will form this aldehyde over here, and this aldehyde, now it will form the aldehyde. I am writing over here, that is this one. Now this kind of aldehyde is going to form, and this OH oxygen molecule will attack over here, and it can form 6-membered intermediate, that is 6-membered lactol type of intermediate, right? This one. Here is your methyl group, and here is your oxygen, here is your OH, and here is your rest part, it remains intact, and here is your methyl. So this is a overall product that we can expect. But there is a side product also formed, that is if this delta hydrogen is going to abstract it, then what will be the major product. Now if this delta hydrogen is going to abstract it, then it can form this kind of that is this CH2 radical. Now this conjugated double bond can be break in this way, and if this break in this way, that is two radical over here, and it recombine to each other. Then it can form, and this in radical will attack with this inner radical, right? Now it can form this type of intermediate over here. That is, here is a double bond and here is a double bond in no way, that is after tautomerization, and it can form, because this is above the plane, so it can form this three membered cyclopropane kind of intermediate over here, and this overall less part is, here is a OH and this part is similar, right? This is how we can expect, and these kinds of examples are quite important of this Barton reaction. Now let's see some previous year question that is very much important for this Barton Nitrite Ester reaction, and that you can easily predict. See, this question was came in CSIR NET June 2016. Now there is a nitrite ester is given and H nu is also given, and we have to predict the what will be the major product of this reaction. Now see, there is, we have to find the delta position, delta hydrogen, and we can do this easily. So this is your alpha position, here is your beta, here is your gamma, and here is your delta, and this is your delta hydrogen. So this is your 1, 2, 3, and 4. So we have to check the fourth position. NO will be the major product. So this is your 1, 2, 3, and 4. Here is your NO group. So this is our major product of this reaction. So this is quite simple, and this question was, I guess this question was came for in 4 marks. So let's see how simple the question was if you do this topic, this Barton nitrite ester reaction. The last example of this video, that is the question was came in the GATE 2021, that is recently. Now this question says that if you have this kind of alcohol, and here is a different types of methyl group is placed over here, and this question comes from this stereospecificity, right? Now, if we can see that this NOCl is placed over here, now we can easily predict this ONO bond is going to form over here, and HNO is given, and we have to find the delta hydrogen in this compound. So this is your alpha position, this is your beta, this is your gamma, and here is your delta. But if you go over here, this is your beta, this is your gamma, and here is your delta, that is, this is your delta hydrogen, and in this case this is your delta hydrogen. Now which delta hydrogen is very much delta hydrogen is important to for this abstraction. Now if you write this compound in this way, that is this one. Now this OH is in this ONO group is above the place, so you can write this ONO in this way. Now if you see over here, this methyl group is in above the plane. Now this methyl group is in above the plane. You can write this CH2H over here, and here is your CH3. I'm not writing this one and this one, but I have to write this one actually, because this is down, so this is below the plane, right? So we can write this H2H is below the plane. So this is your alpha, beta, and this is your gamma and beta. So this is your beta, and this is your gamma, and this is your delta, and here is your delta. Now you can see that this ONO is in above the plane, but this group is below the plane. So it will not form this NO abstraction from here. So it is not our correct option. So we have to abstract this delta hydrogen in this position, because these both groups are is in above the plane. So we have to abstract these hydrogen, not this one. So see, if we do this over here, and here is your methyl group, here is your, and after this NO, it will form this NO, right? And here is your OH. Now it will tautomerizes. So if it tautomerizes, we can write this double bond NOH in this way. So here is your OH, right? So this is your intermediate. Now after this HCl, that is your hydrolysis part. If you do hydrolysis over here, so if you do hydrolysis over here, so you can generate this kind of intermediate, this kind of product, that is your aldehyde over here. Here is your OH, and if you don't do the hydrolysis, I will show you here that how this hydrolysis is going to take place. Because aqueous HCl is given, so H2 is let up over here, it will go like this, then it can form this OH over here, and here is your NH OH. and after that these bonds go over here and it will leave from the system. So finally it will generate this aldehyde over here and plus H2OH. So this is our major product in this case. Now we have to find this major product. In this case, both the aldehydes both are going to form this aldehyde, but not it will form stereoselectively only specifically only this position and only this aldehyde. So option B will be the correct answer during this reaction, right? So I hope this video is very much helpful for you, and thank you so much for watching this video. And if you like this video, share it with your friends as much as you can. So that's it for this video, and thank you so much for watching.